You know, every single engineer hits this wall at some point. Your app is just lightning fast on your own machine. It absolutely flies when you have a few beta testers hammering on it. And then you launch. And suddenly, everything just grinds to a halt. This is the classic scaling dilemma, and how you respond to it really is a career-defining moment. It's what separates the engineers who build resilient, lasting systems from those who just frantically restart servers and cross their fingers. And this isn't some academic theory, right? This is a real production emergency. You can just feel the stress in this message. The symptoms are classic. Totally unpredictable slowdowns, timeouts, and of course, that dreaded flood of user complaints. That 750 millisecond response time, that's not a suggestion. That's a promise they made to their users, a service-level objective, and they're breaking it. The clock is absolutely ticking.
So when the pager is screaming at you and the support channels are just blowing up, panic starts to set in. You start asking yourself, is it the database, a bad deploy, the network, maybe a third-party API we rely on? And here's the thing. Every minute you spend just guessing is another minute of degraded service. And making the wrong call, like, say, buying a massive new database server when the real problem is just one bad line of code, that doesn't just waste time, you're burning budget and creating user trust.
So we're going to tackle this the way a senior engineer would. We're going to build a methodical plan of attack. First, we'll talk about why guessing is probably the most expensive thing you can do. Then, we'll become detectives and figure out how to find the real bottleneck. We'll hunt down the usual suspects, the most common performance killers, and then we'll talk about designing an architecture that actually anticipates growth. And finally, I'll give you the definitive answer to that question. What is the absolute first move you should make?
All right, let's talk about what not to do. In a crisis, the impulse is just to act, right? To do something. But in systems engineering, taking action without data isn't heroic. It's basically just gambling with your production environment.
Oh yeah, these are the classic panic moves. First, point the finger. It's a network problem. Or the most common one, just throw money at it. Let's provision a bigger database, add more web servers. But listen, if your problem is an inefficient loop buried in your code, throwing more hardware at it is like trying to fix a leaky pipe by just cranking up the water pressure. You're not fixing the problem, you're just making a bigger and way more expensive mess.
This slide illustrates the core principle perfectly. Your system is a chain, and it's only as strong as its weakest link. Just look at the numbers here. The front end can handle 1,000 requests per second. The app server, 5,000. But the database chokes at 100. So what's the maximum throughput of your entire system? It's 100. That database is your bottleneck. You could buy an app server the size of a refrigerator and it wouldn't change a single thing. It would just be sitting there, waiting on the database, only faster.
So if gambling is out, how do we win? Well, we stop reacting and we start investigating. We trade that panic button for a magnifying glass. We become system detectives.
This is it. This is the single most important rule in performance engineering. Seriously, it should be tattooed on the inside of every engineer's eyelids. Before you change a single line of code, before you order a single piece of hardware, you have to have data that points you directly to the problem.
And that data comes from a simple three-step process. First, you monitor. This is your high-level dashboard, your CPU, your memory, your network I/O. This tells you what is happening. Second, you profile. This is where you get out the microscope and go deep into the code, timing individual functions and queries. This tells you why it's happening. And finally, you load test. This lets you recreate that fire in production, but in a safe environment so you can actually verify that your fixes work before you deploy them.
Okay, so once you have the tools to investigate, you start to see patterns. And in my experience, the same three culprits show up again and again, especially when you're moving from a small number of users to a large one. First up is the silent killer, the N+1 query problem. So imagine you ask for a list of 100 users. That's one query, simple enough. But then, to show their profile picture, your code loops through those 100 users and makes a separate database query for each and every one. All of a sudden, you've turned one request from a user into 101 database queries. With just a few users doing that at the same time, you will absolutely hammer your database into the ground.
Next up, connection overhead. Think of opening a database connection like making a phone call. There's dialing, waiting for an answer, saying hello. It's a whole process. Now imagine hanging up and redialing for every single sentence you speak. That's what your app is doing when it opens and closes a new connection for every single web request. Pretty soon, you're spending way more time dialing than you are talking, and the overhead itself becomes the bottleneck.
And the final culprit is maybe the most obvious: inefficient data access. You're just hitting the database way too often for the exact same data.
If 10,000 users hit your homepage in a minute, are you really going to run the top 10 products query 10,000 times? That's an incredible amount of wasted work. Look, your database is your most precious and often slowest resource. Your job as an architect is to shield it from unnecessary work.
So, once we've identified these common problems, we can start thinking like architects. How do we design our system not just to fix the immediate fire, but to handle even more growth down the line?
The solution to that inefficient data access is aggressive caching. And these numbers right here show why it's just a non-negotiable part of any scalable system. I mean, look at that in-memory result, a more than 60% reduction in latency. That is the difference between a snappy UI and a frustrated user who just closes the tab. We're moving the data from a slow disk across a network into super fast RAM as close to the application as we can possibly get it. It's an absolute game changer.
And to solve that connection overhead problem, we use something called connection pooling. Think of it as a cache, but for your connections. Instead of creating a new connection every single time, the application just borrows an existing open connection from a ready pool, uses it, and then returns it for the next request. This completely eliminates that expensive setup and teardown cost.
Okay, so after you've optimized your code, you will eventually need more raw power. And this brings us to a really fundamental architectural choice. You've got two paths: vertical scaling, or scaling up, where you make a single server more powerful, and horizontal scaling, or scaling out, where you add more, usually smaller, servers and just spread the work across them.
And the trade-offs here are absolutely critical. Scaling up is simple, yeah, but it's a dead end. There's always a bigger machine you can buy, until there isn't. And worse, you've created a massive single point of failure. When that one giant server dies, your entire business is offline. Scaling out is more complex to set up, but it's the only path to true resilience and massive scale. If one server fails, the load balancer just routes around it. For any application that needs to be highly available, scaling out isn't an option. It's the only option.
Okay, so we've looked at the problems, the detective work, and the architectural solutions. Let's bring it all home and answer that original question. With 5,000 users slowing you down, what do you change first?
And here it is. This is the answer an experienced architect will always give you. The first thing you change is nothing. The first thing you add is the ability to see what's actually going on. You add observability. Because changing anything without data isn't engineering, it's malpractice. So your actual first move is to instrument everything. You install an application performance monitoring tool, an APM, to trace requests all the way from the user's click to the database and back. You turn on detailed query logging so you can see exactly which queries are slow. And you run a profiler on your application code to find the exact functions that are eating up all your CPU cycles. This is how you stop guessing and you start knowing.
This all boils down to one critical rule of thumb for building scalable systems. Never throw expensive hardware at a software problem. Use data to make your code efficient first. Hunt down and fix those bottlenecks. Then, and only then, do you spend money on bigger or more servers. First you optimize, then you scale. That's the principle that separates the systems that merely work from the systems that are built to last.